Are you able to see my screen?
Yes, sir.
Okay. All right. Fantastic. Okay. So what we have is that we last time talked about how to convert from the Earth-centered, Earth-fixed coordinate system to LLH. So if I know what the latitude, longitude, latitude, and height is known, how do I convert from this to the Earth fixed coordinate system, which would be XE, YE, and ZE? We also looked at the idea that if we look at the other way around, the transformation from the Earth fixed frame to the LLH. That is what we looked in the previous lectures. So that is given by this algorithm here. So if we know the XE, YE, and ZE, we compute the L, mu, and H by following the steps of this algorithm, where it is implicit that the latitude and the height are implicitly related, which means that each depends on the other. So the mu depends on the H, and the H depends on the mu again. So therefore, there is an iteration that we have to do until a convergence comes. And we saw that this algorithm is one of the many algorithms that we can use to transform XE, YE, ZE to L, mu, and H. So that was the first transformation from the Earth-centered, Earth-fixed to the latitude, longitude, and height. And then we also talked in the last class how the latitude, longitude, and height can be converted to XE, YE, and ZE. Up to here, are there any questions? Any questions so far? No questions, right? Okay, all right. So let's proceed further. So although latitude, longitude, and height are good enough for us, we are really interested in the transformation between the Earth-centered, Earth-fixed frame. This is the frame in which the GPS measures your measurements, and to transform them into what is called as an Earth flat Earth coordinates, or this is our NED frame. So I want to move from the Earth-centered, Earth-fixed frame to the NED frame. And we understand here that the rotation matrix from N to E is going to depend on the latitude and the longitude values. And I think we talked about this as well in the last class, if I'm not wrong, correct? Yes, no? We talked about this tool in the last class or not yet?
Yes, sir. We discussed about this.
We discussed about this, right? We
Yes.
discussed about this idea that if you want to really look for DP applications, it is good enough to actually construct this plane at a particular L0 and mu0 and formulate the tangent plane at that point. And if the distances which are moved by the vessel are less than 10 kilometers from this point, then this approximation is valid that we can put them into the flat Earth coordinate system. The only difference now is that our rotation matrix will, from all the way to the body fixed frame to the Earth centered frame, can be represented by two composite rotation matrices. One which takes us from from N to E, and another which takes us from B to N. So from the body fixed frame to the NED frame to the Earth fixed frame. And this is good enough for DP applications. And we looked at the idea of how this is performed. So if we know what in the NED frame, how much it has moved, we can compute delta L and delta mu as the change in latitude and longitude as the ship moves about in the NED frame. And that can be computed in terms of how much the x coordinate and the y coordinate of the vessel are in the NED frame, and it multiplied by certain fractions, and these fractions relate to the radii of curvature on the Earth in both the prime vertical as well as the meridian plane. And we saw the expressions for these. These really depend on the ellipsoidal nature of the Earth, and they basically come from WGS 84 model for our Earth. Okay, so if we know, so since these all quantities are known, all I need to know is basically the xn and yn. So if I know the position of the vessel in the NED frame, I can compute the delta L and delta mu and effectively compute what is the new height, the new longitude, the new latitude, and what is the new h. And h can be taken as some reference height minus the Zn value. And that will give me what is the height or the altitude. In most applications, we are not so much concerned about the height, especially in dynamic positioning applications. We are not too concerned about the height. We are really more interested in these two guys. Now, we also tried to talk last time about the opposite, that if I know the new latitude and the new longitude of the vehicle, which is usually measured from a GPS sensor, so I know L and mu, and about some L0 and mu0, I want to form a tangent plane, and in that tangent plane, I want to define an NED system, and in that NED system, I want to know what is the x, y, and z coordinates. Then I simply have to invert these equations which we had before. So all I'm doing now is computing the delta L and delta mu by taking a difference between the measured longitude and the longitude of the reference point. Similarly, the latitude difference is measured as current latitude measured by the sensor minus the reference value of the latitude point, which I'm considering as origin. And then I can use these delta mu and delta L together with the expressions for Rn and Rm to find out what is my x coordinate in the NED frame, y coordinate in the NED frame, and z coordinate in the NED frame. Is it making sense so far? For everyone?
Yes, sir.
Okay, all right, excellent. Okay, so now today we'll try to complete our understanding of kinematics, and the only thing which is left about. So remember that so far we talked about the transformation from the NED frame. So we looked at the transformations between the NED frame to the body frame and vice versa. So we looked both ways. Then we also looked at Earth-centered, Earth-fixed frame to the NED frame. How does the transformation occur? And these two is what we have been looking at in all the previous lectures, up till what we saw just now. Now, the only last thing which we want to look at is between the body frame and the so-called flow frame. Now, this flow frame is relevant because we want to compute the fluid forces, sometimes especially the drag forces or the lift forces. It is convenient to define a frame of reference in the x such that the x-axis is pointing opposite to the direction of the flow. Okay, that is how we define this flow as the frame of reference. Everybody with me so far? It's been a while since we looked at the definition of frame or flow, but it was defined such that the x-axis will point in the opposite direction to the direction of the flow. Does everybody recollect that somewhat? We define this frame as F. We talked about this before, didn't we? Certainly we did. Let me see here real quickly. In the very beginning, when we talked about the reference frames, we talked about the flow frame, isn't it? Such that we align the x-axis with the craft's velocity vector, such that the rest of all the environment is actually being experienced against it. Is that making sense? So suppose if I have a craft, okay, and its velocity vector is pointed this way, then that is the direction in which my xf will be, and followed by yf will be perpendicular to it, and zf will complete the right hand rule in this particular case. I know this has been a while since we covered this, but everybody is recollecting this a little bit?
Yes, sir.
Yes, sir.
Yes, sir.
So what will be the origin of this frame? Where will it be located?
We will typically want to locate this at the body fixed frame itself in most cases. Okay, so origin typically will be at the body fixed frame unless until I specifically want to put it at a different point. So suppose if I'm specifically looking at the rudder flow, I might want to put it at the rudder center of pressure, but it is difficult to know all these quantities ahead of time. So preferable choice would usually be the body's center of origin or the origin of the frame B.
Okay, sir.
Sir,
Yeah.
Sir, will the direction of x-axis be opposite to that of the velocity vector?
No, it will be aligned with the craft's velocity vector. So you will perceive as if the relative to it, the environment is coming the other way. So suppose the craft is moving in this direction with u velocity. Okay.
Yes.
So with respect to the flow axis, you'll see that the environment is actually being incident on the ship by a fluid velocity which is equal to u in the opposite direction, isn't it?
Yes, sir.
So that will allow me to compute what is the drag force in this direction and what is the lift force in this direction. That is why this frame is useful, so that I don't have to worry about the angles when I'm computing the lift and the drag forces. The lift will always be pointed along the negative x direction, and lift will always be pointed about the perpendicular to the x direction, and the drag will be pointed to the negative x direction. So the drag will always be in the negative x direction. Is that making sense?
Yes, sir.
All right. So let me come back here. All right. So the idea here is that xf axis points directly into the relative flow velocity. Okay. Again, just for reference, I'm mentioning here again, the body fixed frame is B with points, the X, Y, and Z axis denoted as XB, YB, and ZB. The NED frame is N, XN, YN, and ZN are the coordinates. So now let's define a few quantities which we are generally always using when we are talking about maneuvering equations. So we'll define those quantities and see what they mean. So let's consider a ship in the picture as shown here. So you see that the ship is oriented this way. Just maybe yeah. All right. So the x-axis of the body fixed frame will be pointed in the longitudinal direction. So let us say that we are looking at from the origin CO, which is the origin of the body fixed frame. So the x-axis is in the positive direction. The y-axis will be in the opposite direction. I think I have messed up a little bit here. This picture is a little wrong because by our convention, the z-axis should point downwards, isn't it? Oh, it is correct. It is correct. Sorry, my bad. Yeah. So y-axis is pointed out perpendicular to the starboard side, and the z-axis will be pointing down in this particular case. Okay, everybody with me so far?
Yes, sir.
All right. The NED frame will have the XN axis, so this is the north direction, and the y-axis will point in the east direction, and the z-axis is pointing in the downward direction. So let us assume that at this particular moment, we have the craft which has a velocity u, which is oriented along this dotted line. Okay, this dotted line that you see here, along which the velocity vector is oriented. And let us say that there is a current in the environment and that the current direction is UC, as given as its direction is given by angle gamma C with respect to the NED axis. So the direction of the current is making an angle gamma C with respect to the XN axis. Is that making sense?
Yes, sir.
Okay, and let's assume that the speed of the current is UC. Then our relative velocity vector, okay, which is defined as the relative to the ship, how is the environment being perceived, will be given by the u vector, which is the actual velocity of the craft minus the current velocity vector. So therefore, this dotted line which you see here, that is UR. Is that making sense? What that vector is? Yes, no. You have to be a little proactive in telling me because I'm looking at my screen, so I'm not looking at your the WebEx meet. So unless you
Sir, is it the resultant vector UR?
correct. So UR is the resultant vector of U and minus UC.
Sir, why should we put the negative sign?
Obviously, because we are looking at relative to the craft how the velocity vector is, right? So the current has to be subtracted from it.
Yes, sir.
Right? So because the current is going in absolute direction, some direction, but relative to the ship, I want to find out what that is. So wherever my velocity is minus the current velocity will be the relative velocity. So just imagine that suppose my velocity was pointed this way, current velocity was pointed this way. I need to subtract the two magnitudes to get my relative velocity, isn't it?
Yes, sir.
All right. Now, we define a couple of angles here. So the first angle that we will define here is called the heading or the yaw angle. Notice that this angle, which is denoted by psi, is the angle between the x-axis of the NED frame and the x-axis of the body fixed frame. So I'm taking the angle between the x-axis of the NED frame and the x-axis of the body fixed frame, and that angle is my heading angle or the yaw angle. The same thing is also called as the yaw angle. And we typically measure this angle using what is called a magnetic compass, or we measure it using gyroscopes by integrating gyroscopes, or having two GPS receivers on board the craft which are located at different points so that we can precisely know what the orientation of the heading looks like. Notice that this angle is defined as positive when we are taking the convention, or its positive orientation is defined with respect to the Zn axis. Okay, with respect to the Zn axis, you have to look at how the rotation is. So since in this case the Zn axis is pointing into the frame, by right hand thumb rule, I can see that it is the clockwise angle which will be having the positive convention in this case. Is everybody with me on that? On the convention?
Yes, sir.
Yes, sir.
The next angle that we will talk about is the coarse angle chi. Okay, it's written as, sometimes my handwriting will be messed up. It should be written as this. Okay, that is coarse angle chi, pronounced as CHI. Alright, this coarse angle is defined as the angle between the x-axis of the NED frame and the velocity vector, the absolute velocity vector of the craft. So the absolute velocity vector of the craft is this vector right here. And we want to find out what is the angle to that from the NED frame. That angle is chi. And this is called the coarse angle. All right. Okay, now notice that this angle is also defined as a positive orientation about the Zn axis. So again, a clockwise rotation in this particular example shown here will be the positive angle chi. Notice that this coarse angle is only defined for non-zero speeds. So whenever the craft has a non-zero speed, only in that case we can define the angle. Because if it has a zero velocity vector, we really don't have a velocity vector to define the coarse angle with. But unlike the heading angle, that is defined whether the craft has zero velocity or a positive velocity. Is that making sense? Yes, no?
So can you repeat that last statement?
Sure. See, the idea here is that the heading angle is defined as the direction between the two x-axes, whereas the coarse angle is defined as the angle between the x-axis of the NED frame and the velocity vector. So since I am having the velocity vector in the coarse angle definition, if there is no velocity, if the ship does not have any velocity, does not have a zero forward speed, does not have a, suppose it has no forward speed, so u is equal to 0, then I can't define coarse angle, isn't it?
Yeah, that's
So that coarse angle is only defined when we have a forward speed of the vessel, whereas the heading angle is always defined. Whether the ship has zero speed or non-zero speed, we will always be able to define the heading angle.
yes.
Okay, all right. Okay, it is easy to see that given the craft velocity is u and v in the body fixed frame, okay, we can find out what is the velocity of the craft in the NED frame by taking components by the angle psi and then precisely knowing how the variation is happening in x and y directions. So this is nothing but a simple rotation matrix with respect to the NED axis to the body fixed frame. Notice here that when I take this velocity vector, so let me draw a new picture here. Let's say this is my craft and it has a velocity vector this way, which is u. This is my xb axis and this is my yb axis. So then this component of the velocity along the x-axis is called u, and along the y-axis this is called v. We already know that, right? So those components velocities, you can now take their projection onto the xn axis and the yn axis, and that will give you the rate of change of position in x, rate of change of position in y in the inertial frame n. Okay, notice that these two quantities on the left hand side are defined in the n frame. Everybody with me so far?
Yes, sir.
Yes.
All right. Now, these velocities can also be expressed. So instead of having as u times cosine of psi minus v times sine of psi, I can multiply and divide by u, capital U. So what will happen? This will become u by u times cosine of psi minus v by u times sine of psi, and the whole thing multiplied by capital U. Now I know that this fellow is actually the angle here, right? It is the cosine of the angle here. Is that making sense? And this quantity v by u is the sine of the same angle here. So if I put everything together, I can show that this thing can be written as u times cosine of psi plus beta c. Yes, where beta c is this angle which we define here. In that case, we know that the coarse angle which we had previously now, so notice that if we go back to this picture, beta c is the angle between the x-axis of the body fixed frame to the velocity vector. Okay, that is this fellow. That is beta c. Okay, and we defined that the coarse angle is the angle between the NED frame's x-axis to the velocity vector. We defined the heading angle as the angle between NED axis x-axis to the x-axis of the body fixed frame. So we can see that this angle here, psi plus beta c, is equal to this one here, which is chi. So we can write chi is equal to psi plus beta c. Everybody with me?
Yes, sir.
Okay. All right. And notice here that the capital U is nothing but square root of u square plus v square, and that beta c angle, we define it as what is called as the crab angle, and that angle is the angle from xb axis, so the x-axis of the body fixed frame, to the velocity vector, and the positive orientation is given by the right hand rule about the zb axis. Okay, so about the zb axis, so which in this case will mean a clockwise rotation. So we are basically considering the angle like this. Okay, now before I proceed any further, I'll come back to this picture in just a minute. So let's proceed a little bit further. Let us say that the current has a velocity UC, VC and WC. Now usually you will probably not have WC as a big component, but locally sometimes the effect may be there, especially if you're looking at underwater vehicles. So to keep it a little general, let us take a current which is looking has three components of velocities, UC, VC and WC. Then the total current velocity, capital UC, is nothing but square root of UC square plus VC square plus WC square. Now that is pretty straightforward. Now, more importantly, what we want to define is that so-called relative velocity vector, or UR. Now that UR is defined as square root of its components, small ur square plus small vr square plus small wr square, where each of these individual components are nothing but the body's velocity minus the current velocity. Is this making sense?
Yes, sir.
Yes, sir.
This is the relative flow. So therefore, we are taking the velocity of the body minus the velocity of the current, and that gives us this relative speed. Okay, now let me come back to this picture here. What I am trying to understand here is that yes, for most of the case, if we are looking at 3 degrees of freedom, we are looking in the planar system here. But when we are actually looking at the 6 degrees of freedom, the craft need not have zero roll angle or zero pitch angle. So it may actually have in the vertical plane also some slant nature, which may cause certain fluid forces to be important. This is particularly important for high speed crafts. So in order to just have a ability to cater to them as well, we will consider what is happening here. So notice here that the z-axis is pointed down. This is the NED down axis, and this is the north axis. And let us assume that that current instant, the x-axis of the body fixed frame is slightly tilted up by a certain angle, theta. Okay, notice that this angle is taken in the anti-clockwise direction. Why is it taken in the anti-clockwise direction? Can anybody tell me? This angle theta, nothing but the pitch angle. Why is it taken in the anti-clockwise direction?
It will be the positive with respect to the y-axis, which is pointing outward of the plane.
Correct. So because our NED plane, if I look at the north is towards the right and Z is pointing down, then the y-axis is pointing out of the plane. So if I consider the right hand thumb rule, the angle will be actually positive orientation will be anti-clockwise. So which is why the pitch angle is denoted here as an anti-clockwise rotation. Okay, so in that vertical plane, you may also have that the actual velocity of the craft need not be in the XY plane of the body frame. In fact, it may be away in the vertical direction also, and that is what is shown here. This here is the velocity vector. That is the velocity vector u. Similarly, the current might have certain components, so the UC vector is also denoted, and the UR, which is the relative velocity vector UR, is also denoted here. Okay, so now let me come back and see what is happening. I'm going to define an angle of attack called alpha. This is the angle between the relative velocity vector to the XB axis. Okay, so I'm looking at between the relative velocity vector, which is this fellow right here that I ticked, and the XB axis. So this angle right here. That angle is defined as the angle of attack. So this is the angle at which the fluid is coming towards the craft in some sense. And if I look at why that angle of attack is important, that angle of attack will tell me what is the lift and the drag force acting on the craft as it moves with a higher speed. So this value of alpha can be denoted as tan inverse of WR by UR, where WR was W minus WC and UR was U minus UC, where UC and VC and WC were the X, Y, and Z components of the current velocity. When the angle of attack is small, we may approximate this tan inverse as just being equal to WR by UR, which usually is fairly a good assumption for most of our applications. Now, this angle of attack is really most important when we are looking at, as I said, high-speed crafts. If not, we are not really too much worried about the vertical plane motions. We are more worried about the horizontal plane motions, which are depicted more in this picture here. Notice that here there is a couple of two other angles which we have not talked about. So one angle is called as the beta or the side slip angle. This angle beta is the side slip angle. And that is defined as the angle between the x-axis of the craft to the relative velocity vector. So where the relative velocity vector is pointed to that, and the orientation is about the positive ZB direction. So that is why you will see that this angle is also clockwise in nature. That is called the side slip angle, or sometimes this is also known as the drift angle. Okay, this angle is also known as the drift angle. Now, in typical naval architecture terms, drift is actually defined as tan inverse minus V by U, whereas the side slip angle here, beta, is represented as tan inverse V by U. Or more so, we should, if we want to be precise, we should write VR by UR. Similarly, this thing is VR by UR. In fact, the side slip angle is actually denoted in terms of minus V by U. So the drift and the side slip angle are slightly different. You see that the main difference is the minus sign. So that is the convention which is normally followed. The drift is what is normally followed in naval architecture terminology. But when we are talking about guidance and control, and we are really talking more about the dynamics and how to control it, it makes much more sense to talk in terms of the side slip angle beta. Now the basic confusion comes due to the fact that both are named beta, and sometimes that causes a lot of confusion. For our case, we will assume that the side slip angle will be denoted by beta, and we'll make sure that that thing is actually defined as tan inverse VR by UR. That is how we will define it and take it forward in our study. So the positive orientation is given by the right hand rule about the ZB axis. Is everybody with me so far?
So these two angles, I got a bit confused. Can you show them on that graph, on that diagram?
Correct. So you need not bother about the drift angle for now. That is not relevant for our case. So I'm going to just take it out so that there is no scope for confusion. Only thing is that this thing was defined in our maneuvering course. And the convention there was that we had a tan inverse minus V by U. Whereas here we are looking at the side slip angle. We are defining that in a convention that we want to define that angle as a positive angle with respect to the ZB axis. And we are looking at how does the, relative velocity vector orient itself with respect to the x-axis of the craft. And this angle is denoted as beta and is defined as positive about the ZB axis. That is all you have to remember.
Okay, sir.
The side slip angle was defined as minus V by U because precisely most of the naval architecture terminology does not have Z in the positive direction as downward, but we typically like to take Z positive in the upward direction. That has been the typical convention in naval architecture.
Yeah. In maneuvering course, we took Z-axis pointing upwards, right? That's why I mean that.
Axis, I don't remember now.
Yeah, it was up only. Yeah, yes, that's why we took minus V by U.
Correct. So that probably explains it, right? So
Yeah.
in typical naval architecture, you will take it that way, but for guidance and control, since we really want to be consistent and keep to the NED frames, orientation, we want to keep the Z-axis pointed downwards. That makes quite easy in certain angles. So therefore, in this case, our side slip angle will be tan inverse VR by UR, now rather than minus VR by UR, which we saw in the other course. Is that clear for everybody?
Yes, sir.
All right, excellent. The same thing I can also define it as sine inverse of VR by capital UR. And when you have a really small side slip angle, beta can be approximated as VR by capital UR. There are a couple of other angles called flight path angle and relative flight path angle. So let's look at, these are defined in the vertical plane. So flight path angle is the angle which your velocity vector makes to the x-axis. Relative flight path angle is what your relative velocity vector makes with the x-axis. And those are the two things which we did not talk about. They are not going to be too much relevant for our purposes. Then, since we defined a side slip angle with respect to the relative velocity vector, we can also define a relative coarse angle, chi r, where that is equal to psi plus beta. Previously, remember that the coarse angle chi was denoted as psi plus beta c, or this was called the crab angle. And this was with respect to the actual velocity vector, whereas this beta is with respect to the relative velocity vector. So let me go back to the picture here to just make it clear. So chi coarse angle is defined as the angle between the x-axis of the NED frame to the absolute velocity of the craft. But if I took the angle to the relative velocity of the craft, that is the relative coarse angle. That is what you see here. Is that clear for everyone? Okay. These are just conventions which we are defining, and these angles are being defined so that later on we can use them when we are talking about guidance, navigation, and control. They won't be so relevant right now, but they will make an impact when discussing about the different angles. It's good to have a name to them so that we can refer to them directly. So in that sense, we are defining all these different angles. Okay. All right, so now that we have defined these angles, now I want to really find out what is the rotation matrix which translates from the flow axis to the body axis. So notice that this flow axis is nothing but pointed about the relative velocity vector typically. And then I want to find out how does that flow axis transform, or how is its orientation different from the body axis. So if I start from the flow axis, I can rotate by an angle minus beta about the z-axis, followed by a rotation by alpha about the y-axis in order to reach the body axis. So for now, let us say the angle of attack is 0, which means that everything is happening in the horizontal plane. So let us say that this angle is 0 and everything is happening in the horizontal plane. So in that case, my flow axis has an x-axis pointed in the same direction as you are. Correct? It will be pointed in this direction. Is that making sense? The x-axis of the flow axis.
Yes.
So if I want to go from here to the XB, YB, ZB frame, I need to rotate by how much angle?
Beta, right?
Beta, but is it positive or negative?
Negative.
Negative beta, right? Because my z-axis is pointing downward, so I am actually going to be rotating in the negative direction, because clockwise is positive about a z pointed into the plane. So I'm going to be rotating by a minus beta angle from the flow axis to reach the body axis. Now, in case suppose things were also happening, things of interest were also happening in the vertical plane, where I had some angle in the angle of attack in my vertical plane, then I would have had to rotate by that angle as well. And notice here that this angle will be positive alpha, because the orientation would be in this way, right? The y-axis is pointing outward, so it would still be anti-clockwise. Is that making sense? I want to go from a velocity, the flow axis which is pointed here, towards here. So I need to rotate by angle alpha, but in the positive orientation. Okay, so that is why you see that when I want to go from the flow axis to the body axis, I first rotate by an angle minus beta about the z-axis, followed by a rotation of plus alpha about the y-axis in order to reach my body fixed frame. So this intermediate frame which we get, I refer to that as the stability axis. So that is what we are calling as the stability axis. Just a name given to it, it will not have much implication on other things. Okay, now when we are looking at what is the lift and the drag force, it is easy to compute it. We can compute that as half rho, the relative velocity square, times a reference area, which is generally usually the projected area that we are interested in, times the drag coefficient, which is a function of the angle of attack. Similarly, the lift force also can be given as half rho ur square times S times SL, where CL, where CL is the lift coefficient, whereas CD is the drag coefficient, and both of them depend on the angle of attack alpha. Okay, for surface ships, when we are dealing with mostly ships which are floating on the surface, this value of alpha will typically be close to 0, which means that everything is happening more or less in the horizontal plane. We're not really looking for things which are happening in the vertical plane. The vertical plane really becomes important when we are dealing with a submerged vehicle. So in that case, we have to look at what the alpha looks like. So given that I know what my lift and drag forces are in the what you call flow axis frame, I would like to transform them into the body fixed frames, this one, right? I would want to know what are the forces acting on the body in the body fixed frame. So let us consider that where the drift angle or the side slip angle is 0, okay, in that case I only have the angle of attack to account for, and I can simply take the drag and the lift forces and then multiply by a rotation matrix which purely depends on alpha to get my forces in the body fixed frame. Is this making sense?
Yes.
Now can someone tell me why do I have these minus signs here?
The force directions are opposite to the.
So let me go back to the picture here. Correct. So when I have this flow, the relative flow coming into the picture, right? So I will have the lift acting in which direction? Will it act in this way or this way?
First one.
This one, right?
Yeah.
And that will be opposite to your z-axis.
Yes.
So that is why the negative sign for the lift force. What about the drag? The drag will occur in the direction of the velocity, which is opposite to how your x-axis is defined. That is why it is defined as minus drag. That's why the minus sign. Okay, I hope that is clear for everybody.
Yes, sir.
All right. Okay, but now let's do the full transformation. Here we looked at what happens when beta is 0, but let's say when beta is not 0, how do we go ahead with the transformation? So we again use our vectorial notations which we had defined previously. We know what is the velocity, relative velocity in the body fixed frame. We multiply that by an angle rotation matrix about y-axis by an angle alpha, and we reach the stability axis. We reach what is the velocity, relative velocity in the stability axis. And from there, from the stability axis, we would like to go by another rotation matrix by z-axis about minus beta angle to reach the flow axis. Okay. Remember that when we are going from the flow to the body fixed frame, we said the rotation by z followed by a rotation by y. Now, if I'm looking at the other way around, from the b axis to the f axis, I'll do a first rotation by y followed by a rotation by z. Is this making sense?
Yes, sir.
So therefore, the composite rotation matrix to go from body fixed frame to the flow frame is Rz minus beta rotation matrix times Ry alpha rotation matrix. Those rotation matrices are nothing but what we are very familiar with. We simply put them in, multiply them out. This is what we should get. Now, the velocity, the relative velocity in the flow axis is nothing but ur00 because we orientate the flow axis such that all the velocity of the fluid is in the x-axis direction, right?
Yes, sir.
So the velocity in the body fixed frame, if it has components ur, vr and wr, we simply multiply by this rotation matrix in order to get those values. So if I want to calculate VBR, I'll take the rotation matrix from B to F, take a transpose of that and multiply that by the velocity in the flow direction. Is this making sense?
Yes, sir.
This is the velocity in the F frame. This is the velocity in the B frame. So I need a rotation matrix which goes from F to B. I know the rotation matrix which goes from B to F. I just take a transpose of that and multiply. So eventually you'll get three expressions for UR, VR and WR from there. Now, when we have small angles of orientation, then these angles are relatively smaller and you can see that UR almost turns out to be equal to capital UR, VR turns out to be beta times UR, WR turns out to be alpha times UR. When the angle of attack and the side slip angle are small, then we can approximate these if the angles are really small. Does that make sense so far?
Yes.
Okay, so that completes our, yeah, any questions? I thought I heard someone's voice. Was there a question? No question? I thought I heard someone say something and I think I interrupted them inadvertently. No, okay, all right. So that completes our discussion about the kinematics. So we have really talked about how the transformation occurs between the different frames. We defined the different frames: Earth-centered, Earth-fixed frame, and then we talked about the NED frame, and then we talked about the body frame, and then we discussed about how does this transformations occur, how do this transformations occur, and then we also talked about how these transformations occur. Okay, so far notice that we have only talked about the kinematics, which means that we are really only concerned about the positions, velocities, and accelerations. But we have really not talked about any of the dynamics. Dynamics means you need to talk about what are the forces, what is the force which causes these kinematics. Those we have not talked about. So that effect only we have discussed. We really didn't talk about the cause for those effects. And that cause is what we are going to focus next when we will be deriving the rigid body kinetics in our next class. So when I say kinetics, that includes the forces and the equations of motion. So we'll look at how we define the 6 degree of freedom equations of motion. So 3 translational and 3 rotational equations of motion for any general rigid body uh, which is operating in the vessel, in the sea. How do you figure out what are its governing equations of motion? And those will be useful for us when we are doing control. So before we can start to control a vehicle, we need to understand its dynamics properly, and this is what we'll be discussing in the coming lecture. Okay, so that is all for today. Any questions so far on whatever we covered till today? Okay, let me stop recording.